day, I'm Dr. T and welcome to my office. So today I would like to start a video series on astronomy. As usual, this is going to be a brief overview, an introduction for those of you who are going to become educators, specifically in the K-8 range. As usual with these overviews, I would like to start out with a little bit of further reading and further watching, as the case may be. So Complexly did a crash course astronomy, so I'm going to recommend Complexly's crash course astronomy. Additionally, OpenStax has an astronomy textbook if you're looking for a formal astronomy textbook. Now, going beyond that, I am going to suggest The Light Ages by Seb Falk. Falk? I'm not sure how to pronounce his name. This one is a discussion of medieval science, specifically astronomy. So very much a kind of UK or Eurocentric point of view from a time that historically we think of as a primitive dark age, a time of recession, which it was definitely not the strongest economic time, and there was a lot of social challenges during this period. But he makes the point that science didn't die. Science very much kept progressing. Our understanding and scholarly work was still a thing. And additionally, this is going to be a little bit less relevant for this particular video, a little bit more so for the next one. But I'm going to recommend the excellent YouTuber Scott Manley, as he has a wonderful channel on aerospace, focusing primarily on technology. His early videos were Kerbal Space Let's Plays, and then he moved on to explaining content, and wonderful. He knows his stuff. So I do suggest checking out Scott Manley if you are interested in more of the technical side. Okay, so in this video, what I want to do is talk about the sky, kind of what we can see, what prehistoric peoples would have seen when looking up into the sky. Now, I do want to make a couple of caveats. One, I'm going to say prehistoric peoples because prehistoric peoples would have been able to see this, but frankly, through most of human history, this was still relevant. So by prehistoric peoples, honestly, I'm including most historical individuals as well as, depending on their lifestyle and location, people who are still alive today. See, the thing I want to separate out is that in our modern world, we have lots of distractions. Things like social media and other demands that are drawing our attention every which way. And we're not able to pay attention to the subtle, simple patterns. Likewise, artificial light is now both a thing and quite cheap. If we go back even 100 years ago, artificial lighting, say candles and whatnot, that was expensive. And as such, you couldn't just light up the night. Now, we routinely just turn the night into day with artificial lighting. And this means that, well, we never really experience the night. It gets dark, but when it gets dark on a clear sky, you can see an awful lot up in the sky. And that's something that, in general, we can't observe. I've known people who were literal astronomers to go out and go, whoa, what's that? And they were looking at the Milky Way. And as such, what I want to do here is to kind of discuss what it looks like without the distractions and without the light pollution. Now, one of the first things that we're going to also think about is how can we use what we see in the sky for a practical application? The wonders should not be undersold. Looking out at nature and seeing the wonders around you is definitely a thing and definitely valuable. But if we understand what's going on, we can also have some somewhat more practical, more concrete applications here. And let's start with one of the ones that is still quite relevant to us today, and definitely one that I use whenever I need to mow grass. Okay, so what you'll notice is that the sun travels in an arc across the sky, rising in the east, going somewhat overhead, and setting in the west. Now, to be clear, we're the ones moving. The sun is, from our point of view, relatively stationary. Now, the sun is going around our galaxy, and we are going around the sun in our orbit, and then the Earth is spinning on its axis. And when it comes to the arc of the sun across the sky, it's going to be that last one that's relevant. There's a point that Galileo Galilei made. I'm going to kind of transform it because he used horses, but I'll use cars. But the idea is that all motion is relative to the observer. If I'm in a car and I'm driving down, I see the speed limit sign, and hopefully its number somewhat matches the thing on my dashboard, well, it's going to look like it's coming towards me. It's going to zoom past me. It's not moving. I'm moving. But from my point of view, everything around me, the speed limit sign, the people, the telephone poles, they all look like they're moving past me. In reality, I'm moving forward past them. So we want to kind of keep this dichotomy. I'm going to change points of view throughout this video and think about our view as someone on the Earth, as well as, well, a point of view of the Earth or the point of view of the sun. So let's get back to the sun's motion across the sky. The Earth is spinning, and as such, we're on the Earth and we're going around the Earth as a nice big circle. And so as we're rotating, everything else that's away from the Earth that's not spinning looks like it's rotating as well. So it looks like everything in the sky is doing a big circle around us. You can actually see this with the stars as well. There's a form of photography called star trails. It's definitely kind of cool. I've tried it a little bit myself. It actually is a pretty advanced technique, and I have not been successful. But here's an image, and the credit for the person who took the image, of what's called a star trail. And so the idea here is it's a long exposure photograph. You point the camera at the sky, you put it on a good tripod, and you just open up that shutter and let her cook. Quite often these are actually composite images, so you do multiple images and then you smush them together in photo processing software. But because this exposure time is very long, anything that moves in a frame while the camera is actually taking the picture is going to be all blurry. It's going to be streaky. You can sometimes see this with cars. You can see the headlights forming streaks, etc. Or someone who's moving if the shutter speed is relatively slow. Well, when you do it with stars, they form these circles. And they're going to form a circle around one of our poles, either the North or South Pole. I believe this image is the South Pole. And well, that is a reflection that they're not moving, the camera is moving. The camera is on the Earth and everybody's spinning. But we can use this to our advantage because the sun is a star. It's one of those things that's going around us because in reality, we're going around. And as such, we can actually use this to our advantage. You'll notice the sun goes up in the east. It's going to take time to cross the sky and sink in the west. If I look at where the sun is in the sky, maybe I shouldn't look at the sun. Maybe I should look at where a shadow is being cast from a stick or something. That way I don't actually burn out my eyeballs. Well, what I'll notice is that stick will mark and it will cast a shadow and that shadow will arc across. And well, I can use that as a progress bar. The further that shadow is gone, the sooner the day is to being done. And I probably need to get back to camp and in an environment so I don't fall off a cliff because it got really, really dark. This is the beginning of timekeeping, or chronology if we want to be fancy. We're going to start observing the sky and the stars and whatnot, and by doing so, we can pay attention to what time it is. How much day do we have left? Typically speaking, the ancients would have taken the hours of the day, and they wouldn't have been fixed units of time. They would have been relative, because it turns out the time it takes the sun to arc across the sky does vary depending on the season, for reasons we'll get to here shortly. But that length of time, the hour, was simply a percentage of the day. As such, it wasn't a fixed number of minutes, which were a fixed number of seconds. It was a percentage of the day. During the winter, when the days were shorter, an hour was shorter. During the summer, when the days were longer, the hour was longer. Now, by the way, you can do the same thing with the stars. Because keep in mind, we're the ones moving. Everybody else is just kind of sitting there. One of the interesting points that's brought up by the author of the Light Ages is that medieval monasteries would quite often have a series of set prayers, and one of which was done before sunrise, which means you need to know when to do that. When do you wake everybody up to get on and go for the religious service and then have breakfast and move on to whatever else you're doing? Well, the way you end up doing is you watch the stars in the sky. Probably assign this task to this sounds like the lowest ranking guy there. You know, this is one of those like, oh, you're the new guy. Yeah, you're stuck with the worst job. This is, at least in my mind, I don't know. Maybe it wasn't the new guy. Maybe it wasn't, you know, the most junior monk present, but I suspect it was the most junior monk that got stuck with the job. And it basically was, here, go stand there. You don't get to sleep tonight, or maybe you have to get up really, really early. And watch for that star, and when it goes over that barn or that tree or whatever thing, wake everybody up, ring the bell, that kind of stuff. We got to get going because by the time that star has gotten to this point, yeah, it's pretty much good to go. And this is the same idea of using a sundial. A sundial is just measuring the sun's shadow, but you can do the same thing with stars, although you generally don't get a good shadow off of a star. You can get a surprisingly good shadow off of a full moon, though. I will say that. Okay, so we can get this idea of timekeeping, what time of day it is, and this is incredibly valuable. But we can also go for what time of year it is, and there's a few options that we've got for this. For starters, if we look at the sun's path is going to go from east to west, but it's not going to go like east, straight overhead, straight back to west, at least not for most of us. If you are north of the tropics, the sun will always be to your south. So actually keep that in mind. That's going to be a useful piece of information here in a second. But during the winter, when the Earth's axis is tilted so that your hemisphere is pointing away from the sun and the sun's light is kind of spread out more, the sun is going to look lower down on the horizon. Likewise, during the summer, the sun is going to be higher up in the sky because you are pointing towards the sun. Now, if you're north of the tropics, the sun will always be south. If you are in the south of the tropics, the sun will always be to your north. And if you're in the tropics, and this is like why the tropics are the tropics, the sun is going to go pretty much over your head. And there's actually an interesting day. It occurs twice a year, unless you're right on one of the tropics, in which case it only happens once a year, where the sun goes directly above your head. Directly above your head is what we call your zenith. Below your feet is what we call your nadir. And when the sun reaches your zenith, that means your shadow is directly underneath you. This is called Laha Noon. I've not experienced this in person. I've only seen pictures. I'd love to head to Hawaii, the only state in the US that's actually within the tropics, where they do have a Laha Noon, but because your shadow is below you, you can't see your shadow. You're standing on it. It's no shadow day. Yeah, things look like they're badly photoshopped, even though that's completely real. It's definitely an interesting idea. Something that, as someone who lives north of the tropics, I don't get to see on a regular basis, like ever. Okay, so as the sun's going up and down, that increases the amount of light we are getting. We can actually see this from this photo, which is from a satellite that's sun synchronous, so it's looking at the Earth and it's always staying on the sun side. It's over probably at what we call L1, which I'll get to in the next video, but there's a couple of points where you can put satellites that are relatively stable, and sometimes they're not exactly around Earth per se. And this one's between the Earth and the sun. During the winter, you can't really see that much of that hemisphere illuminated. Whereas during the summer, that particular hemisphere is illuminated quite well because it's pointing towards Earth. And of course, spring and fall, it's a little bit more of a 50-50, a nice even split between those two. Which is, of course, why the weather changes. During winter, we get less light from the sun. The days are shorter because we're kind of pointing away from it. And the light is more spread out. So less light means less heat. It's going to get colder. Now, if you're far north, it's going to be a much more extreme effect. If you're just a little bit north, it's not that big of a deal. Likewise, if you're far south, it'll be a more extreme effect, or just a little bit south, not nearly as much. But the idea here is that in the winter, you get less light, it's going to be colder. And in the summer, more light, more heat, it's going to be warmer. So you can track the motion of the sun in the sky. The higher the sun is in the sky, the warmer it's going to be. So as you mark the motion of the sun in the sky over the course of the year, you can start planning out what the weather is going to be doing. We know as the sun is going down, it's going to be getting colder and colder, and as the sun goes back up, it's going to start warming up again. Thus, we can get a general idea is that once the sun at noon reaches a certain height, maybe it's a good idea to start planting. Or once it dips below a certain height, we better start thinking about harvesting. The crops better be ready, or possibly we need to harvest some of the livestock. It's expensive and difficult to maintain your entire herd over the winter, so generally you harvest, kill and butcher, a good chunk of your livestock and only have the breeding ones over the winter and give them food. And that way you don't have to feed as many and you get a bunch of preserved meats, etc. for the winter. What we've noticed is that prehistoric peoples and historic peoples would use this knowledge and build in calendars into some of their architecture. So if you have a long tunnel, well, it only is going to become illuminated at the other end when the sun lines up with the tunnel. As such, you can line up your tunnel such that the sun lines up with it only during certain parts of the year and those that are particularly important to you. Over here is an example of what's known as the sun dagger. This is in Chaco Canyon National Park in northern New Mexico. What you end up seeing, this is an illustration. I could not get a copyright free image that was of kind of the whole thing. I really wanted to. I found several great images, but they weren't. They were all copyrighted, and I couldn't use them. But what you've got in this area is this petroglyph. So someone a long time ago, we're thinking maybe about 1,000 years ago, took a rock and banged into the side of this bluff a spiral and a couple other decorations. And they did so rather creatively. See, what you can't see here is that there's a couple of big boulders. And they're kind of overlapping and they're casting this in shadow, except for there's a couple of gaps between the boulders. And they create these beams of light that shine on the wall. And so what the artist did was he pounded out, or she, we don't know who the artist or artists were, but what the artists did was they pounded out a spiral such that during the summer, it's going to be lined up nice in the middle, and then on the winter solstice, you're going to get the sunlight flanking the spiral. And so you can tell the time of year based on where the light lands on the spiral. But of course, the sun isn't your only option. So instead, what you could do is look at the stars at night. See, when we're looking at stars, some stars are what we call circumpolar. Basically, from our point of view, they're over the poles, and thus they're going to go spinning around the poles, kind of like the star trails that were in that picture behind me that you saw earlier. But other stars are equatorial. These are positions closer to our equator, and, well, they're kind of in line with the orbit of the Earth, which means that, well, keep in mind, we're looking out away from the sun at night. Well, if the star is on the other side of the sun, we're not going to see it at night. So instead, we see one set of stars during the night during the winter, and a different set of stars at night during the summer. And so we can see which stars we see at night, and that can tell us how we've progressed through the year. It's generally a good idea, whenever we're thinking about time, to think of it as more of a progress bar. Actually, that's the trick on reading the old analog clocks, is you think of them as a progress bar through the day, not necessarily the actual time that you're seeing. Now, this is a fairly useful trick. If I know what stars are up in the sky, that gives me an idea of what I need to be doing. Do I need to be planting? Do I need to be harvesting? Is it time to party because I got nothing else better to do? Or maybe it's time to harvest the sheep or the cows or what other critters else I might need to do. Likewise, if I'm eating migratory animals and I'm hunting, where do I need to travel if I'm migratory, or what animals might be migrating in towards my area that I need to go harvest? The classic is that the dog days of summer are named after the dog star. When the dog star becomes visible, we are in the dog days of summer, which is the hotter part, but they're named after the star that we can see. Of course, memorizing a whole bunch of random points of light is an absolute pain. So how do we do with this? Well, what we end up doing is we draw patterns. We humans are all about stories and all about patterns. So we connect the dots. There's tons and tons of stars, so we'll connect the dots and we'll make patterns. We call these patterns constellations. These are entirely a human construct. They're just points of light. Sometimes the stars are close to each other, sometimes they're nowhere near. They just happen to line up in an angular way, but one might be relatively close and one might be very, very, very far away. But as humans, we line up the stars and we make patterns and we tell stories about them. This helps us remember what we're looking for and to know what stars we are seeing. Now, when it comes to the stars in the night sky, we can use them very much for what time of year it is, but also we can use them for where we are at. Keep in mind, we are sitting on a big old sphere. And as such, well, where we're at is going to change our angle to everything else. So if we're up at the North Pole, we're going to not be able to see the stars that are visible from the southern hemisphere because there's a planet in the way, Earth. And the stars that we see, some of them will be very much directly above us. Very conveniently, if we're straight on the North Pole, very close to our zenith is going to be Polaris, or the North Star. Dumb luck, it just happens to line up with our axis, and that's really convenient. There isn't a South Star, unfortunately. There is ways to do and figure out where the South Pole is from the southern hemisphere, but it's a bit more complicated on the southern side because it's not this very conveniently placed star. Now, if we are standing upon the North Pole, as we walk in any direction, we're going south. As we go south, the North Star will no longer be at our zenith. But we can measure our angle to the North Star and the horizon, and that will tell us where, in terms of latitude, we are, at least for the northern hemisphere. Once you get to the southern hemisphere, though, there's a planet in the way, Earth, again. So you won't be able to see the North Star, but you will be able to see other stars. As such, this gives us a couple of pieces of information. One, if we are able to see Polaris, that's going to tell us which way north is. Once again, there are stars you can look at in the southern hemisphere. They're just not quite so convenient. But by observing where Polaris is, that's going to tell us which way north is. And of course, if you know which way north is, you know which way everything else is. And second, it's going to tell you your latitude. Remember, the latitude are going to be the bands running around the circle going north and south. They're the latitude. Longitude is a slightly different story, and that one I will get to here in a little bit because that took a good deal of technology to sort out where you are going east and west. But if you know where Polaris is, then you got a general idea of where it's going. By the way, Polaris is at the tip of the Little Dipper. This is where the narrative follow the drinking gourd comes from. If you look at the Large Dipper and you look at kind of the two stars from there, you can line up with the tip of the Little Dipper and you can figure out where Polaris is. Side note, there is some controversy with that song. It is thought that that was used to communicate to escaped slaves which way to go, basically follow Polaris, go north to freedom. Unfortunately, there's no record of Follow the Drinking Gourd existing in the 19th century. The earliest records date to the early 20th century, and, well, it kind of needed to exist before general emancipation, otherwise it can't really do leading people to freedom kind of thing. But with that aside, you get the general idea. You can follow a star. Now, if we are trying to figure out where we are east and west, it's a little bit more difficult of a problem because keep in mind the Earth is spinning, and so, well, all the stars are moving east to west, including the sun. So we need to figure out where we are, and the way we're going to actually do that is we're going to use the fact the Earth is spinning to our advantage. We're going to need to know a 0 point. Historically, we've picked Greenwich, England for our 0 point for longitude, but, well, it could actually be any place. And in history, it's actually been quite a few different locations. The British Empire picked Greenwich, England, because that's where they had the royal astronomy, but every other empire had their own choices. Now, if you know the time at Greenwich, England, and you know the time where you are at, you can compare the difference. Local time's fairly straightforward. Sundial, pretty easy. Figure out when noon is. If you know the time over there, you compare the difference in time, and that tells you how far around the Earth you are, because, hey, Earth rotates every 24 hours, so for every hour, you're 1/24th of the way around the Earth. Unfortunately, trying to figure out what time it is over there when you're not there is a bit more inconvenient. Nowadays we have satellites and clocks, etc., so everything works great, but back in the day, that was not quite the case. Clocks typically ran with pendulums, and pendulums are great if you're not moving, but if you put the thing on a boat, the pendulum and the boat rocking is not going to go well together. And so there was the prize for how to figure out longitude. Well, the solution was a very nice pocket watch. The chronometer was a well-crafted pocket watch, one that instead of going tick, 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 goes tick, 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 and as such is able to handle the rocking and the rolling of a boat. Okay, replace the battery. Now, for the eagle-eyed amongst you, you've probably been noticing that a lot of what I've been describing is describing the location of stars or the sun in the sky. And you might be thinking, hey, we're making an awful lot of triangles, aren't we? From the horizon to my eye to whatever star we're talking about? And the answer is yes. Yes, we are doing a lot of triangles. And that means I want to be able to measure angles. And I can look at a lot of timekeeping, but definitely navigation, and a lot of the progress in technology for that has historically been the ability to measure angles. The most primitive forms would be observing, say, a shadow relative to a stick, or maybe where the sun is or stars are relative to things around the environment. So basically adding another point to my triangle here. And that works surprisingly well. You can get a lot going for you there. And if you look at a lot of ancient archaeology, and honestly even some modern stuff, it's pretty obvious they were set up to align with various stars during various times of the years. But buildings are not exactly all that portable, so we maybe want to have something a little bit smaller, a little bit more portable to measure our angles. And as such, we can start looking through history as we start seeing the ability to measure angles improving. One I would like to point out is the kamal. I'm probably mispronouncing that horribly, but it's this guy. It's literally the Arabic word for stick. And the goal here is you take a plank of wood, you put a hole in it, and then you take a string and you run that to your chin. And so now you have the length of the wood that's going to create one of your sides of your triangle. The string is going to create the other side of the triangle. And as such, then that's going to set your angles. And so now you can use that to match up with the angle of a star, such as the North Star, but not necessarily, to the horizon. This was used quite often with the Indian trade wind. So if you look at the Indian Ocean, it has an interesting feature. During half the year, the winds go east to west, and the other half the year, the winds go west to east. So if you are in, say, the either India or the Arabian Peninsula, and you want to trade with people on the other side, you can get in your boats when the wind is going the direction you want to go. You travel across, you wait 6 months, the wind changes, and you travel the other way. Fairly convenient. Now, as you're going up and down the coast, you can stay pretty much in target by, making sure you're following the coast. That way you're not lost in the middle of the Indian Ocean, because it is a big place, and if you get lost there, we're not finding you. But you would like to know how far up and down the coast you're going. I mean, you could stop and say hi, but not necessarily would there be people to say hi to and give you directions. And, just like these days, you stop some random person and they may or may not actually give you good directions or not, or they have any idea what language you're speaking. So it would be nice to be able to figure out how far north or south you had been by measuring the angle to the sun or various stars. You take the board, you line it up with the horizon and your star, so that measures the height above the horizon. You stretch the string out. Wherever it meets your chin, you tie a knot. That way you've got yourself an angle. So now as you go sailing back, you start constantly measuring the distance between that star and the horizon of reference. So now you know if you are north or south of where you need to be. Okay. And then you do the same thing for different ports. You either make a different board with a string, or you put multiple strings on the same cord attached to your board. That way you got a general idea of, are we there yet? Or have we overshot our port, and do I need to turn around and go backwards? Now, of course, there are other ways to do this. We could have more of a sphere with a targeting line, and hold that up so it acts as a pendulum to get nice and flat, and you got yourself an astrolabe. you can actually start turning these into analog computers in many cases. Later on, we end up getting the sextant, which uses some mirrors to make it a bit more compact, and then also gives you a little bit more information because these guys are actually analog computers built into your angle measuring device, which gets dreadfully convenient. Now, let's look at a few other things that we would start noticing up in the sky, and one of those is going to be the moon. It's kind of big and bright. It's big in that it's relatively close to us. Compared to the other things in the sky, it's relatively small, but it is very close to us, so it's going to look quite large. So a few things you'll start noticing. The moon isn't always looking the same way. Sometimes it will be fully illuminated, what we call a full moon. Sometimes only a little tiny bit of it will be illuminated, a crescent moon, and sometimes it just won't be illuminated, a new moon. Well, let's think about why that is, and then how could we use this to our advantage? Well, for starters, so where's the light coming from? The moon doesn't glow. It's closer to a parking lot, so it needs to be illuminated by something, and that something is going to be the sun. So as the sun shines on the Earth, but the moon is going around the Earth, so the sun is going to shine on the moon as well. And, well, as such, the part of the moon that's getting shined on is going to be bright and shiny. The part that is not. So, the part that's illuminated is going to be the part that is pointing towards the sun. Now, the moon is going around us. As such, the part that we see may be the part that's illuminated. It may not be the part that's illuminated, or good chance some of what we see will be some of what's illuminated. Hence, we get the different phases of the moon. Basically, how much of the moon that we can see, from our point of view, is illuminated. We can use this, one, to track time. The moon takes roughly about a month to go around us. That's kind of the point of a month. It's the time the moon takes to go around us. And also, as the moon's going around us, well, it can do a couple rather interesting little quirks. See, the moon's going around us due to our gravity and its motion. It's orbiting the Earth. Well, it has gravity too, and it is pulling on the Earth. So, the moon is going around the Earth, but the Earth is also going around the moon. The Earth isn't making very large circles because we're a lot bigger, so the moon is more going around us than we are around it, but we are still going around in a bit of a circle with respect to the moon. We also have a lot of water on this planet, and in fact, most of it's kind of connected. If you look at the oceans, it's more like the ocean, not oceans. And so the water can start flowing. The moon's gravity is pulling on the Earth, both the rock and the water, but the water flows a lot more so than the rock, and so as the moon's gravity pulls on the Earth, the water's going to flow towards the moon. It also flows away from the moon, because keep in mind, the Earth is wobbling, and so as the Earth is orbiting around a point between us and the moon, it's closer to us by a lot, the water on the back half is kind of not quite keeping up, and it's sloshing to the back. So we get this bulge of water that can be surprisingly high. One on the moon side and one on the opposite side. We call these high tide. Of course, this water had to come from somewhere, and so there's going to be the low tides, which are going to be 90 degrees off of the Earth-Moon axis. Now, these bulges are relative to the moon, so they go around once a month, like the moon does, but the Earth is spinning, and so we go through these bulges, well, each bulge once a day. There's 2 bulges and 2 dips. So if you're by a coastline, as you start coming around the bulge, the water's going to start rising. As you're going away from the bulge, the water's going to start lowering. But the moon isn't the only thing that we're orbiting. We're also orbiting the sun. It's a lot farther away, but it is a lot heavier, and so it's going to do the exact same thing. It's going to create bulges. A high bulge on the sun side and opposite the sun, as well as a lower bulge at 90 degrees. Now, sometimes those bulges are going to line up. In that case, we're going to get a particularly high tide because the 2 bulges are adding to each other, and we call that a spring tide. Likewise, sometimes the 2 bulges are going to be misaligned, and we're going to get less dramatic of a high tide and less dramatic of a low tide because the bulge from the moon is lining up with the dip from the sun, in which case we call that a neap tide. Now, if you're doing anything with boats and the shore, this is kind of a big deal because the shore is effectively moving, or the water is moving, getting closer or farther away from the shore. So this is going to be particularly important for you with your boats. If you think about the invasion during D-Day, this had to be timed with the tides in order to get across the shore optimally. So, following the moon does give you a clue into what your tides are going to be, as well as a nice way of separating out the year so that you can do useful things that you might want to do on, say, a monthly basis. Months are kind of convenient. Now, if you also look at the night sky, you're going to notice a couple other things. Every now and then, the moon goes red. What's up with that? Well, this is an eclipse. This is going to be a lunar eclipse. The Earth got in the way of the moon. So we lined up Sun, Earth, and Moon, and we lined them up nice and perfectly. This doesn't happen every full moon because the moon's orbit isn't lined up with the Earth's orbit around the sun. It's a bit off kilter. So most of the time the moon goes a bit above or a bit below the Earth's shadow, so it doesn't line up and doesn't get into the shadow. But every now and then the moon lines up with the Earth's shadow. But why is it red? Well, we have an atmosphere. And while the Earth's shadow is blocking the light from the sun, some of the light is able to bend around the Earth thanks to our atmosphere. Also thanks to our atmosphere, it's going to do a much better job with the red colors of the light. And so it's effectively in the sunset from all around the Earth. As such, it's going to be a reddish moon. Now, of course, the moon could be on the other side when it crosses over. So instead of a full moon, when the Earth, Sun, Moon line up, it could be a new moon. In which case, it's going to get between the Earth and the sun, and its shadow will be cast on the Earth. If you happen to be living in that area, it'll appear the moon is going across the sun, and it will get dark. A partial eclipse is kind of cool, but not that big of a deal. You definitely need those glasses things because, once again, you don't want to burn out your eyeballs. But a total eclipse? Ooh, those are exciting. It is so weird. You get to see the atmosphere of the sun, the corona of the sun, which is awesome. Something you don't normally get to see because, once again, trying to look at the sun would burn out your eyeballs. But not if the moon's in front of it. Also, it goes from midday to dark back to bright daylight in a fairly short order. If you get the chance to go see a total solar eclipse, totally do it. Partial eclipse, not that exciting. Total eclipse, those things are cool. Okay, so I want to end this video talking a little bit about how we describe where things are in the night sky, or the day sky, as the case may be. And there's kind of three ways, and I've already talked about two of them. One is going to be your local coordinate system. And actually, by the way, there's like a dozen different ways of doing this. I'm only going to talk about three. The first one is your local coordinate system, or azimuth and altitude. I already mentioned how your zenith is directly above you, and your nadir is directly below you. Azimuth is how far, starting with north and going to east, it is in the sky. So something that's due north would have an azimuth of 0. Something that is due east would have an azimuth of 90 degrees. Remember, we're doing a lot of angle measuring here. It's all about the triangles. Altitude is how far above the horizon it is. 0 degrees on the horizon, 90 degrees straight up at your zenith. By knowing this, you can tell someone standing next to you where the star is, or you can program that into your telescope. If your modern telescopes, if they know where they're oriented, you can program in and they'll go ahead and point it towards you. Side note, most telescopes will have a tiny little clock motor. It's dropped down to half speed because clocks rotate once every 12 hours. You need to do this every 24. Because remember the star trails chart? Yeah, if your telescope doesn't have a tiny little motor in it slowly changing its angle, whatever you point it to, in a little bit, well, its angle will be changing because it's hooked to the Earth and the Earth is rotating. Now, azimuth and altitude is a great way of describing where things are, but if I want to communicate where things are in the sky to someone who isn't necessarily right next to me, where I am at, the star will have a certain azimuth and altitude. If I'm someplace else, it'll have a different azimuth and altitude depending on where that someplace else is on the Earth. Obviously, if I'm not on Earth, it's all going to be completely different. So how can I coordinate with somebody who is not right next to me? Well, one, I could say which constellation it happens to be near. We get a whole bunch of these things. They kind of make a patchwork out of the sky. So I could describe something being in a certain constellation. We did this with the first black hole. We call it Cygnus X1 for the first black hole that we discovered, and that's in the Cygnus constellation. Okay, so let's say we want to communicate with anyone on Earth, which is most everyone, where something is up in the night sky. We need a coordinate system that is relative to Earth, not relative to where we're located. In this case, we're going to use an equatorial coordinate system, or right ascension and declination. Declination is basically space latitude. The equator extends out, that's going to be 0 degrees declination. North Pole would be 90 degrees declination, and South Pole would be -90. So we're basically doing latitude expanded out. Let's talk longitude. In this case, we're not going to try and do the longitude expanded out because that keeps moving, but we need a nice 0 point for doing this. And to do so, we're going to look at where the sun is in the sky on the vernal equinox. That's the one that happens in March. The equinox is when the day and night are equal because the sun's location in the sky is directly above the equator. The solstices are where we are at the extreme end of our tilt, and the sun is going to be directly above one of the tropics. For right ascension, we are going to do the sun's location at the vernal equinox, which is March, and then the declination is going to be north versus south relative to where the equator is. Declination is given in degrees. Right ascension is given in hours, minutes, and seconds. Okay, so with that said, I'm going to wrap up this video with the night sky, and in later videos, I'm going to discuss getting to space and what space looks like if you zoom out away from Earth. So with that said, have a wonderful day, and I'll see you in future videos.